Good morning, guys. Okay. Sorry, let me get some of my own notes out of the way here. So we can get started. Today we're going to talk a little bit about parametric equations. I think, though, that there was an example. Let's see, is that here? It's not. There's one example from your homework that I was asked about over the weekend in an office hour that I wanted to talk about in class, but I think it was, let me double check and see. I think he was in this section, yeah. So I'll go ahead and do that with hopes that he arrives here soon. But the rest of the day today is going to be spent working on parametric curves, which is definitely something that deserves its own time. So I'm going to get moving fast because we're going to do an extra little homework problem here today. Actually, rather than diving right into the homework problem itself, I wanted to look at sort of the bigger picture issue around the homework problem. I tried to say this a few times last week, but I don't think I really communicated it effectively. That when it comes to these arc length problems, the best thing you can do is approach them and sort of think about them in the same way that you approach and think about the volume problems from chapter 6. What I mean by that is every time I solve one of these problems, I like to draw the picture and imagine rotating that little ds element. So I have some curve. And just for shits and giggles, let's suppose this time that I wanted to revolve around the y-axis. Here's my little arc length element, the thing we call ds. And if I wanted to find the surface area of this solid, say, bounded from like, here to here, if I wanted to find that surface area, I would be rotating this region. And the game here, now that I'm not rotating about the x-axis anymore, changes in a meaningful way. And there's more than one way to think of this. So remember, you can characterize a point on a curve either as x comma f of x, or as, I'll write it, g of y comma y, g of y comma y. Right, like the square root function, I could either call that, x comma squared x, or y squared comma y. Either one would work. Here, if it's easy to think of your function as a function of y rather than as a function of x, one of the ways to attack this would be to just swap all the variables x and y in our formula. But I wanted to sort of just show you all the different things we can do. If you imagine rotating just this ds segment of arc length, then you would get that sort of band. And you can always get at these problems by thinking about them like this. So this would be my advice, is to draw these little things if you're ever uncertain. Which I can cut and unroll. And I just have to think about the dimensions of this band. One of them is clearly still ds. I'm going to go back to the blue here. But another one, there's this radius still. And so this dimension would still be the circumference, which is 2 pi times that radius. But now that radius is this distance. Rather than this vertical distance. So in our original formula, remember, we had 2 pi f of x, or 2 pi y, times ds. Now, this distance is the horizontal distance from the y-axis to this point, which is either you could say it as r equals x or r equals g of y. So your ds, the thing you need to integrate for arc length, dA, the thing we need to integrate for surface area, is 2 pi r ds, which could be two pi x ds or 2 pi g of y ds. And ds, arc length, can also be thought of a couple different ways, but most of the time we're going to think of this as 2 pi x and the ds piece as being f primed of x all squared plus 1. But if the curve happens to be neatly expressible as a function of y, you could also think of it as 2 pi g of y times g primed of y squared plus 1 dy. Your book does its best to try and put all these formulas into a single thing. Really, last week, I only gave you the one and then told you, you can think about it in the same way that you think about the volume problems. And this is what I meant when I said that. So if you change your axis of rotation, or if you change the variables that you're given, like maybe they give you x equals some combination of y's, then you can use any one of these approaches. This really boils down to like 4 different approaches. Characterized in terms of x, rotating about x or y. That's 2 different ones. And then characterized in terms of y, rotating about x or y. Your book does describe all of these. So if you're feeling a little bit lost in that homework, if you need some more time, that's fine, of course. As always, just submit an extension request. But if you want to see the breakdown of all the possible combinations of these things, they are here. So boxes 5 and 6 there give the full formula, where this piece is ds. This piece is ds. They use the Leibniz notation instead of the prime notation, dy dx, that is f primed of x. Dx dy, that's g primed of y. And then here they give 2 alternate ways of writing it. I like this with the ds. So if you're rotating about the y-axis versus rotating about the x-axis, and then each one of these, you can use ds as either one of these guys, depending on whether your variable was given you nicely in terms of x or in terms of y. I just wanted to share that and invite you guys to think about it in this same sort of way. So if you're looking at a surface area problem and you're struggling with how to set it up, draw the picture, draw in this little ds arc length element, and then imagine rotating just that little ds arc length element about your axis of rotation. So if I rotate just this little pink piece, then I will get this little pink band, which I could then cut and unroll. And this, of course, is the circumference, which is 2 pi r. This is still ds, because that's what it was originally. And from there, you can build up your formula. dA would be 2 pi r ds. And in this particular instance, where I'm rotating about the y-axis, I can think of that radius r as two different things. If I was given my variables all in terms of x's, then I would say, oh, okay, well, r is just this horizontal distance, so that has to be x right here. So I get 2 pi x ds, and I would write ds then in terms of x. Or if I was given this curve in terms of y, I would say r is this horizontal distance, which has to be g of y. Again, it's the x coordinate that's giving it to me. It just depends on how the point is characterized. So I could write r as this if I had the variable x everywhere, and I could write r as this if I had the variable y everywhere. And then use the form of ds that sort of matches with the variables that you have. Okay, today though, we're going to start talking about some much cooler stuff, in my opinion. Today we're going to talk about parametric curves. Officially, this is section 10.1. We may get to 10.2. They're both on parametric curves. I think I had time to introduce these to you guys last week, but just to recap, a parametric curve is a graph of a set of equations that look like x equals x of t, y equals y of t, where there's a time domain specified, and these may be strictly less than or less than or equal to. I'm going to write them as less than or equal to for now, which are called parametric equations. The variable t, which usually represents time. By the way, I usually think of this as a moving particle. The variable t, which usually represents time, is called a parameter. And hence the name parametric. The main idea here is that x and y are no longer linked directly to each other. Okay, Zach, thank you for the heads up. Yeah, so the main idea here is that x and y are no longer linked directly to each other. Usually when you have a graph or a curve, it's coming like y equals f of x. You've got like some equation that tells you how x and y are related to each other, and then that's what determines your graph. That's what determines your curve. No longer is that the case, which means no longer does your curve have to obey any of the sort of nice relationships required between x and y. Specifically, y doesn't have to be a function of x anymore, so no more vertical line test. X doesn't have to be a function of y anymore, no more horizontal line test. These can look like any curve imaginable. So just to kind of draw what a random parametric curve might look like, you would make a table if you didn't know what else to do. And when you plug in the earliest t value you're allowed to plug in, you plug that into x and you plug that into y, and that will give you an ordered pair. This would be x of a, comma, y of a. So x and y aren't linked to each other anymore, but they are linked to this variable t. And then you can plug in a bunch more points, and your curve might do something like this. You plug in a bunch of other t values. Who knows? Maybe some crazy bullshit like this. And then you end over here at x of b, comma, y of b. And they have a direction. So as t increases, you can think of this as a path. Right, you can think of like a little ant that starts at this point at when t is equal to a and walks along this path in this direction as t runs from a to b. So that's why we think of t as time usually. This point over here is called the initial point. And this point over here is called the terminal point. So when I ask you to graph a set of parametric equations, this is what I'm looking for. I'm looking for something like this. I want to see the initial point labeled. I want to see the terminal point labeled. I want to see the curve. And I want these little arrows indicating direction. I'm going to show you how to do this. I'm going to show you how to come up with these graphs. And I'm also going to show you how to take a graph that you already know from like the function setting and turn it into a set of parametric equations, which is pretty cool. The act of taking a curve that you already know and turning it into a set of parametric equations, or writing down a set of parametric equations for a curve, is called parametrizing the curve. And it's very important in Calc 3. Also important in complex analysis and certain areas of physics. But the first place you'll see an application is Calc 3. So let's look at some examples. Maybe to start, we'll keep things somewhat simple. Let's sketch the parametric curve defined by we'll do x of t equals t plus 2 and y of t equals 4 minus t squared, where about negative 6, 7, fuck it, negative 10 is less than or equal to t is less than or equal to 10. Okay. So I have an equation for x and an equation for y. They don't tell me how to go from an x to a y or from a y to an x. They both tell me how to go from t to x or from t to y. So if I wanted to do this by plotting points, I would need to make a table, t, x, and y. So let's do that. -10, let's do maybe, oh, hammy, it's okay. Maybe I'll go by 2's, -8, -6. That's going to be too much. We'll just jump around a little bit. Then from here, maybe we'll go to, I don't see any harm in it. Then we'll jump to 10. How about that? Okay. So I was thinking we'd go from -10 to 10 by 2's, but that's too many points. I'm lazy. So we'll go -10 to 0 by 2's, and then we'll skip a few between 4 and 10. If I plug in -10 to this equation for x, so I take this -10 and I plug it in everywhere there's a t in the x equation. -10 plus 2 is -8. And if I plug -10 into the equation for y, oh, this is out of control, isn't it? Yeah, 4 minus -10 squared. That's 4 minus 100. That's -96. So some of these I won't. We'll just do it. If I plug in 8 for t, -8 plus 2 is -6. And 4 minus -8 squared, well, -8 squared is 64. 4 minus 64 is -60. If I plug in -6, -6 plus 2 is -4. -6 squared is 36. 4 minus 36 is -32. If I plug in -4 for t, -4 plus 2 is -2. If I plug in 4 for t, 4 minus -4 squared is 4 minus 16. That's -12. -2 for t, then x will be 0. And 4 minus -2 squared is 4 minus 4. That's also 0. If I plug in 0 for t, then x is 2. And y is 4. If I plug in 2 for t, then x is 4. And y is 2 minus 4 again. That's 0 again. If I plug in 4 for t, then that's 4 plus 2 is 6 for x. And 4 minus 36 is -32 again. And if I plug in 10 for t, then 10 plus 2 is 12 for x. And 4 minus 10 squared is 4 minus 100 is -96 again. So these would be the ordered pairs, -8, -96, -6, 60, and so on. I'll sketch this, but I'm going to use some scales that are a little bit big. I see there's a question in the chat. Oh, did I make a mistake somewhere, Maggie? Y of 4 is -12. Oh, yeah. Thank you. Yeah, you're correct. We're not plugging 6 in for t. We're plugging 4 in. Thank you. Okay. So I need these y values to go all the way down to like -100, but we're going to take big steps. We'll call this -100. Should make this like -50. And we'll kind of approximate. My x values, we'll say 2, 4, 6, 8, 10, 12. And now we go 1, 2, 3, 4, 5, 6. Now we'll do it like that. Okay, -2, -4, -6, -8, -10, -12. So we're starting at -8, -96, which is way down here. That is my initial point. And then we move to -6, -60. And then we move to -4, -32. Which I guess would be right around here. And then we move to -2, 12. And then 0, 0. And then we have 2, 4. 17 is 0, 2, 4, yep. And I'll do the same thing out here. We'll go by 2s, 2, 4, 6, 8, 10. So after 2, 4, we have 4, 0, which would be right here. And then 6, -12 would be symmetric with 2, -12. And then 12, 96 would be way out here. Yep. So 2, 4, 6, 8, 10, 12, 96. So you can kind of see what this shape is, right? This is a parabola. Modulo my bad art. And as t increased, we went from this point to this point to this point, so my arrows are going like this. So this is the graph of these parametric equations. Or equivalently, these parametric equations give what we would call a parametrization of this graph. And I think the first question that should be coming to mind when we look at that, is there any better way besides making a table, right? I mean, when we first start off learning mathematics, this is how we graph all sorts of functions. We make a table and we plot points and we connect the points. And we hope that we plotted enough points to get enough detail that our shape is correct. That's what we do at the very start of college algebra and in 1033. But then we very quickly develop better methods, right? In pre-calc and calc 1, we learn all these other ways to graph functions. So is there a better way to graph parametric curves? Interesting question. Before I answer that definitively, I'd like to take a look in Desmos just to sort of show you. I'm going to enter this as an ordered pair, x, y. Oh, let me see. I should be able to get, no, here, okay. -10 to 10. And then I wish there should be some way for me to introduce a slider. But yeah, here you see it, right? Here's our parabola. The vertex is at 2, 4. It's opening down. We have roots at 0 and 2. What was the question there, Maggie? Oh, weird. All right. says it should be sharing. Sometimes the screen share does weird stuff like that. Okay, here we go. So I'll run you back through this then. So what we do is we enter this as an ordered pair. The x was t plus 2, right? That was my x equation. So I entered as an ordered pair x comma y. T plus 2 comma 4 minus t squared. And then I can specify my time domain here, which was -10 to 10. And you'll see exactly what we had. I can rescale the y-axis a little bit. All right, and you see it. There's our picture. My initial point is over here. My terminal point is over here. Now there is a way to get these to play nice. What is the trick here? Yeah, no, it's not giving me the option to do it like that. All right, we'll play with it more later. But that's the idea, is if you want to, you can think of these as ordered pairs, x comma y, where the x equation goes in the first ordered pair and the y equation goes in the second spot of the ordered pair. And you can just verify that, yes, the graph we drew is correct. But it won't give you the direction, and it won't tell you which point is terminal, which point is initial, anything like that. It'll just help you verify that your picture is correct. Another fun one to play with. Actually, maybe before that, let me grab an example from your book. I don't want to move too quickly here. Yeah, that's okay. Oh, no, okay, we'll go right there, fine. All right, no harm. And here, let's go from let's go from negative pi over 2. I don't know, we'll go from 0 to pi. This will be more interesting, and it'll start off monotone, which is easier. So here, x of t is cosine t, and y of t is sine squared t. My time domain is 0 to pi. And I'll do the same thing by plotting points at first. So I make a table. And here the t values that I want to plug in are going to be nice things to plug into trig functions between 0 and pi. So I could do like 0, pi over 4, pi over 2, 3 pi over 4, and pi. When t is equal to 0, cosine of t is cos of 0, that's 1. And the sine of t is 0, because the sine of 0 is 0, and 0 squared is still 0. So we're starting at the point 1 comma 0. When t is pi over 4, the cosine of pi over 4 is root 2 over 2. And sine squared of pi over 4 is 1/2. Sine squared is root 2 over 2 all squared. which is 2 over 4, which is 1/2. When t is pi over 2, the cosine of pi over 2 is 0. And the sine of pi over 2 is 1, so sine squared of pi over 2 is 1 squared, which is still 1. When t is equal to 3 pi over 4, the cosine of 3 pi over 4 is negative root 2 over 2. And sine squared of 3 pi over 4 is still 1/2. And when t is equal to pi, the cosine of pi is negative 1. And the sine of pi is 0, so sine squared of pi is 0 squared, which is still 0. So here my x's are going from 1 to negative 1, and my y's go from 0 up to 1, then back to 0. Maybe I'll mark this as 1, 1, and negative 1. At time t equals 0, I'm at the point 1, 0. So we're starting over here. This is my initial point. At time t equals pi over 4, I'm at the point root 2 over 2, 1/2. Which one of these is bigger is not super duper obvious when you write it like this, but remember root 2 over 2 is just a fancy way of saying 1 over the square root of 2. The square root of 2 is a little bit smaller than 2. It's like 1.4. So its reciprocal is a little bit larger than the reciprocal of 2. So this is like here, root 2 over 2. And 1/2 is halfway between there and there. So we're at like a point like this. And then we're all the way up here to 0, 1. And then we go to negative root 2 over 2, 1/2. I'll do my best to draw symmetric. And then we're back here to negative 1, 0. So my curve, again, looks parabolic. And this time I'm starting over here, marching my way along like this. This would be my terminal point. You could look at Desmos for verification. We let t run from 0 to pi. Oh, I should rescale my axes. There it is. And again, it does kind of look like a piece of a parabola. Interesting. We might start asking ourselves why. Why did both of these two curves we looked at appear parabolic? Before I answer that definitively, I'm going to do one more example. Just one more. Questions on this fellow? Okay. Last example before we look a little deeper. I'd like to again use some trigonometry. And this time I'm going to write it as an ordered pair. So x of t is cos t, and y of t is sine t. Just getting you used to the notation. I could give you the curve like this. And let's say now that 0 is less than or equal to t is less than or equal to 2 pi. I'm choosing this example to introduce this notation because I'm hoping it will remind you of something. But we can make our table. Here I'll do multiples of pi over 2. From 0 to 2 pi. So when t is equal to 0, x of t is the cosine of 0, that's 1. Y of t is the sine of 0, that's 0. When t is pi over 2, x of pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. When t is equal to pi, the cosine of pi is negative 1, the sine of pi is 0. When t is 3 pi over 2, the cosine of 3 pi over 2 is 0, the sine of 3 pi over 2 is negative 1. And when t is 2 pi, cosine of 2 pi is 1, sine of 2 pi is 0. Can anybody tell me what it is I'm going to draw here? Yeah, it's kind of reminiscent of alternating stuff, sure. I mean, it is blinking positive, negative here. But think about these ordered pairs. Think about where you've seen ordered pairs of this type before. Let's go ahead and plot these points. Let's call this 1. So my first ordered pair is 1, 0. So this is my initial point. My next ordered pair is 0, 1. My next ordered pair is negative 1, 0. And then my next ordered pair after that is 0, negative 1. So I'm going like, and then, and then, and then, no more than that. Yeah, this is the unit circle. Where have you seen ordered pairs of the form cosine, sine before? It's the unit circle. All right, and if I had included like pi over 4 and pi over 6 in here, these would have jumped out at you right away as the standard like root 2 over 2 or root 3 over 2 points. You would recognize them immediately, I'm sure, which is why I didn't. Yeah, this is a parametrization of the unit circle, where your initial point is the same as your terminal point. Parametric curves where your initial and terminal point are the same are called loops. And this certainly isn't the only loop. There are lots and lots of loops. Not just circles, but anything where you run around and end up where you started is a loop. Why is this the unit circle? Well, one of ways to think about it is that, yeah, you know the unit circle is all the points cosine, sine. This is still the x-axis. This is still the y-axis. There is no t-axis here. But another way to do this, another way to discover this, is to do something called eliminating the parameter. That's where you do some amount of algebra with these things until the t's go away. So here, we know that cos squared t plus sine squared t is equal to 1, right? This is a true statement about sine and cosine. But cos squared t, that's x of t all squared. Sine of t, that's y of t. So sine squared t is y of t all squared. In other words, this is the equation x squared plus y squared equals 1, which we know is the unit circle. So here I could use the trig identity, cosine squared t plus sine squared t equals 1, to go from the pair of equations involving t to a single equation involving x and y. I want to show you how to do this in the other two examples we looked at also. Does everybody feel like they understand what happened there? Don't mind the question, how did you know to do that? For now, let that sit as a mystery, and I just ask, are you comfortable going from this line to this line? So cosine of t is x of t. So cos squared of t is x of t all squared. Similarly, y of t is sine t. So sine squared t is y of t all squared. Well, then x I just call x of t x, call y of t y, and say, okay, this relationship is true if and only if this relationship is true, where x and y are these functions, cosine and sine. Let me show you how this looks on the last example. So the way this will be phrased in the problems is eliminate the parameter to get an equation involving x and y. Can we eliminate the parameter here? Well, here y of t is sine squared t. And by the first Pythagorean identity, sine squared t is 1 minus cos squared t, which is 1 minus x of t all squared. So this is y equals 1 minus x squared. And would you look at that? If you think about the graph y equals 1 minus x squared, that is this parabola, right? It just goes on and on and on forever, rather than stopping here. And if we go back to that very first example, we can do a similar thing there also. I'll show you in just a second. Any questions on this or the previous example, actually eliminating the parameter? This can be a useful trick for drawing the graphs. That's where I'm going with this. I may not know what the graph of, this parametric equation set looks like right away, but I do know what 1 minus x squared looks like. So if I do this first, then I just have to figure out what portion of that graph and in what direction is my parametric curve traveling. All right, let's go back to that first example. This guy. And rather than plotting points, again, let's eliminate the parameter. Here, things are a little bit easier. There's no trig. It's all just algebra. So if I solve this equation, I know right now that x of t is equal to t plus 2. I can stop writing the of t. I'll just write it as x equals t plus 2, which is the same as saying x minus 2 equals t. And now plug this into y. So I know y is 4 minus t squared. So I'll stop writing the of t, just y equals 4 minus t squared. And then everywhere there's a t here, I can put in x minus 2. So y is equal to 4 minus x minus 2 squared. And you've got yourself a quadratic in x and y. We could clean this up a little bit. This is y equals 4 minus x squared minus 4x plus 4. So that's the same as y equals, the 4's will cancel. Let's see. Yeah, you get negative x squared plus 4x. Which again is the equation of this parabola. So if I didn't want to take the time to plot all these points and get my curve, I could have done this first. And that would have told me what my curve looked like. It would have told me that I'm on this parabola. And then I just have to figure out my initial point and my terminal point. Let's try doing one of these eliminate the parameter moves. Where we haven't drawn the graph first. So last call for questions on what we've done eliminating this parameter t. Okay, then I'm going to reach into the book for some more examples here. No graphing devices. Certainly not that yet. Points indicated now. So just eliminate the parameter, find the Cartesian equation. All right. Let's try number 7 here. T squared minus 3, t plus 2. I'm going to write down the problem and then I will. Oh no, let's do one of 11 through 18. Those look more fun. Yeah, those look much more fun. How about 14? So I'll write this down. Sketch the curve x equals e to the t, y equals e to the negative 2t, where no time domain is given, by eliminating the parameter t. Okay. So if they don't specify t values, they don't give you an interval of t values to use, you're free to assume that t runs from negative infinity to infinity. Here they told me x of t is e to the t, y of t is e to the negative 2t. So is there any way I can take these and get rid of the t's to get a direct relationship between x and y? That's the question here. Any ideas? We could come here and solve the x equation for t. Yeah. If you take the natural log on both sides, this says that the natural log of x is equal to the natural log of e to the t, which is just t. And now plug this in to the y equation. Y is e to the negative 2t, which would be the same as e to the negative 2 ln x. Is there any more I can do with this to clean it up? Would you agree that this is the same as this? Yeah, good. Using the exponent rules, right? Remember that the natural log of a to the b is the same as b times the natural log of a. So this negative 2 can come inside the natural log as a power. And then e raised to the natural log of some shit is just that shit. So y is x to the negative 2, or 1 over x squared. So our graph is not necessarily the whole thing, but some portion of the curve y equals 1 over x squared. So 1 over x squared, what does that look like? Well, there's a piece over here, and there's a piece over here, right? As t goes from negative infinity to infinity, what sort of x values will this spit out? Will this ever spit out a negative x value? It won't, right? As t goes to negative infinity, e to the t goes to 0. And as t goes to positive infinity, e to the t goes to positive infinity. So even though y equals 1 over x squared has another piece over here, that piece is not a part of this parametric curve. My parametric curve is just this piece. And we're going in this direction. Because as t gets bigger, e to the t gets bigger. And as t goes to negative infinity, e to the t goes to 0. So my parametric curve here is just this portion of y equals 1 over x squared. Just like with our parabola, we didn't get the whole parabola, we just got part of it. It had a terminal point and an end point. Here, I don't have a terminal point and an end point because the t's are allowed to go from negative infinity to infinity. But that doesn't mean x's go from negative infinity to infinity. X's go over the range of this function. Is this making sense? Okay. Let's see. Again, we can verify in Desmos, no harm in that. So this was e to the t for x and e to the negative 2t for y. And my t's are allowed to run from not 0, but negative infinity to infinity. Oh, this doesn't like that for some reason. Now let's try a negative 10 to 10. And let's try resetting our scales here. Okay. Oh, why isn't this playing nice? Oh, negative 10 to 10. There we go. Yeah. All right, and just like we did, you get the one branch of the y equals 1 over x squared. So here's the whole thing. Here's our guy. Whole thing, our guy. So this business of plotting a parametric curve is important. I give you some parametric equations. You plot the curve. Really, the direction that's going to be fun to go is I give you the curve and you come up with the parametric equations. So the last thing I'm going to leave you with here today is how to parametrize a curve. In other words, how to come up with parametric equations. This is not as hard as it may sound, as long as the curve is given in the way we're used to curves being given, where x is a function of y or y is a function of x. Then you can parametrize it as x of t equals t and y of t equals f of t. I'll let you think about why that's the case. This is like saying just x equals t and y is f of t. So the points t comma f of t would be exactly the same as the points x comma f of x. Or for your x's, you could use something like the natural log of t. And y of t, you could use f of the natural log of t. Or for x of t, you could use tangent. And y of t would be f of tangent t. The important thing here is that the function you choose for your x's has range, all real numbers, and is 1 to 1. All right, you really need a 1-to-1 function whose range is all real numbers to be sure that you can parametrize any curve using that as your x. And you'll have to specify the t values that give you the portion of the graph you want. So for example, if I wanted to parametrize the graph of y equals, let's say the how about natural log of x, where 1 over e is less than or equal to x is less than or equal to e squared. We could do that a bunch of ways. The easiest way, and this one right here is usually called the standard parametrization. The simplest set of parametric curves that will do this is x of t equals t, and y of t is the natural log of t, where 1 over e is less than or equal to t is less than or equal to e squared. Another way to do this would be to say x of t is, we can use this one, the natural log of t, and then y of t would be the natural log of the natural log of t. And then here, to come up with my t values, I would have to think about what inputs for t correspond to these outputs for x. And I would have to think about that for just a second, actually. This would be e to the 1 over e is less than or equal to t is less than or equal to e to the e squared. Kind of silly looking. But these would be two ways, this set of equations with these t values, or this set of equations with these t values, to parametrize this curve. Let me just for fun start with this one. I'll show you in Desmos. We'll begin with the curve that we know we want, which is y equals ln x. And I said we were going to pay attention to the interval 1 over e is less than or equal to x is less than or equal to e squared. All right, so here's the portion of the curve I'm trying to parametrize. Let's try plotting t comma ln t, where t runs from 1 over e to e squared. Same thing, right? So these parametric equations, this is x of t equals t, and y of t equals ln t, give me the exact same graph as the thing I was asked to parametrize. Now, I claim that we could also do this as ln t comma ln t. And then here, we would have to go from e raised to the 1 over e power up to e raised to the e squared power. And there you see it again. This time I'll put it in green. So both of these are parametrizations of this same curve, which is a portion of the whole natural log function. Why won't this show up on top? Select this one down. There we go. That's not the only way to do it. What else could we do? We could do e to the t comma t. And here, t would have to run from -1 up to 2. And again, you see that this green is the same as the green or red from earlier. So there's a bunch of ways to parameterize any given portion of any given curve. The standard parametrization says just use t for x, and then let y be f of t, where f is the function whose graph you're trying to parameterize. But really, you could use any one-to-one function whose range is all real numbers for x, and then just plug that thing into f to get your y's. As long as the y value is f of the x value, you will be on that graph. And then it's just a matter of selecting the right t values, right, the right time domain, to give you the portion of the graph that you wanted. Okay. I don't think there's anything else that I wanted to browbeat you guys with on this stuff. It's all pretty fun. You can think about where x is increasing and decreasing with respect to time. You can think about where y is increasing and decreasing with respect to time. And you can use those things to help you figure out where you have vertical tangents, where you have horizontal tangents. And that will lead us into what we're going to talk about on Wednesday, which is doing calculus in this setting with parametric curves. The other thing I'm going to do on Wednesday, besides figuring out tangents, I'm going to show you how to do arc length with parametric curves. And I'm also going to run very carefully through this special example of a cycloid. Now, a little bit of extra homework for you guys. Please do yourself the favor of reading example 7. I didn't want to show this to you today because the notation that the textbook uses, I want to use the same notation, but it could be intimidating because they're using the variable theta for the parameter instead of t, and it's kind of a long derivation, but cycloids are an extremely important family of curves. If you've ever heard of the brachistochrone problem, kind of the path along which a ball would roll fastest from point A to point B under the influence of gravity, the cycloid is an important part of that solution. If you've ever watched someone ride by you on a bicycle, and they have those little reflectors on their wheels that spin around with the wheels, and you've noticed the sort of cool pattern that that reflector makes, that is a cycloid. So next time we're going to start by cooking up the parametric curves for a cycloid, or parametric equations for a cycloid, which are here, but they take a little bit of work to understand. It's a kind of complicated geometric derivation. And then we're going to talk about arc length. We're going to talk about arc length and tangents of parametric curves. And that's all we're going to do from parametric curves, tangents and arc lengths. I will also show you how to get areas, but areas in the parametric setting are not exciting. There's nothing you can do by thinking about parametric curves with areas that you can't do otherwise in the regular setting. Then we're going to move to 10.3, which is talking about polar coordinates. Totally different coordinate system. We're going to talk about how to solve the area problem here, because there are some problems where areas are hard to calculate in the regular XY coordinate system, but easy to calculate in the polar coordinate system, weirdly enough. So that's where we're going, lads and ladies. And then the very last thing we're going to do is 10.4 on areas and lengths in polar coordinates. And that's the end of Calc 2. So this week we are going to go through 10.1 and 10.2. We did pretty much all of 10.1 today. We're going to do a little bit more on Wednesday. Wednesday we will wrap up 10.2 by talking about the calculus operations on parametric curves. And then in our final week, I will show you polar coordinates, which should be a refresher from your pre-calculus and trig class. And then we'll talk about how to find areas in polar coordinates, and that will be it. Any questions for me before I let you guys go for the day? All right, remember, we do have class on Wednesday. I know it's getting close to the holiday, so I'll ask you to please be good. Please come to class and take notes, even though we're all getting turkey crazy. And I wish you guys all the best. I will see you next time. If you do need more time on last week's homework, go ahead and pop an extension request. I will have my normal office hours this afternoon, so if you need to talk to me, we can talk there. Otherwise, send me a Canvas message or something like that if you need to chat, and take care of yourselves.